Hi, I'm Elise Madonna, and I'm going to be talking about a paper called Slot Machines, Discovering Winning Combinations of Random Weights in Neural Networks, and this was included in the ICML conference of 2021. So first, for a really brief overview of the general idea of this paper, it was inspired by traditional slot machines, which spin reels to find a winning combination, and each reel has a fixed set of symbols, like the picture I've included on the right. The neural net algorithms can be made to simulate a traditional slot machine by having a fixed subset of random weights for each connection in the network, and then having an algorithm spin a reel to select a weight value for each of those connections. However, you have to have a good selection method in place for this idea to work. So the one that's used in this paper optimizes the given loss at each of the spinning iterations. So some previous work that's been done in this field started in 2019 with the lottery ticket hypothesis. And the idea behind this study was to use sparse subnetworks in a randomly initialized neural network. Each of the subnetworks will be trained in isolation from scratch, and the results show that this approach achieved better than chance performance, and the subnetworks were able to achieve similar accuracy to a trained dense network. So they work by assigning a probability value to each connection, and those probability values are then used to sample the connections, and they can be updated using a stochastic gradient descent. Another approach is pruning at initialization, which was completed by Lee in 2020. The idea behind this is kind of similar to pruning a decision tree. Basically, an entire randomly initialized network is created, and then some of the connections are pruned. However, this approach is different from the ones used in this study because the pruning aspect is eliminated, and instead of selecting connections that define a subnetwork, this study actually just uses all the connections in the network. So all the connections remain active instead of selecting just a few of the connections. Finally, there was the approach of random decision trees, which is pretty popular just way to implement random feature subset selection. And as I mentioned, it's often used in creating decision trees. This approach inspired the slot machine approach taken by this paper. However, this paper has adapted the random decision tree approach to the training of neural networks by restricting the optimization of each of the connections over a random subset of weight values. So it's the same idea as using a subset of features at each split in a random forest decision tree, but it's just applied to neural nets instead. So the question and proposed solution from this study. First, the question basically boils down to, can a network created with random weights compete with the same model using optimized weights? And the author's proposed solution is to construct non-sparse neural networks that achieve high accuracy by selecting a value from a fixed set of random weights for each connection. So basically, the initial findings show that a simple procedure which just uses a small number of random weight options for each connection and does not change the weight values can have pretty good accuracy and be potentially less computationally demanding than more traditional neural network options, which might iteratively update the weight as the model is trained. And the basic goal is to just find neural networks with random weights that match the performance of those traditionally trained networks. The main difference being that this slot machine method would train by just selecting from a subset of available random weight values. And the intuition behind this is that if the weights for a network are drawn from an appropriate distribution, then a non-zero probability exists that the network will obtain good accuracy on a given task. And this results from selecting a good combination of connection values by optimizing loss. And I'll talk a little bit more about the specific algorithm on the next slide. So the algorithm works by doing a forward pass and then a backward pass. Basically, the overview is that the algorithm allocates k fixed random weight values to each connection, and then assigns a quality score to each of these values. So then in the forward pass, these weights can be selected based on the quality scores, and then the backward pass, they can be updated, and after that, the weights are never changed for the model. So in the forward pass, this is the selection function equation. Either a greedy selection can be used or a probabilistic sampling selection, which I've included on this slide. Basically, the selection function inputs the quality score of a weight as returned to the other possible k weight values, and then it returns k minus 1 values. So the selection function is sampling from a multinomial distribution. The greedy sampling method was used in some of the experiments I'll talk about, but that one alternatively uses the index corresponding to the largest score, so it's more computationally demanding than this probabilistic sampling equation that I've included here. But either can be used. And the k values are considered during training for each connection, but only one value per connection is used during testing, just as a note. And the weight for each connection is determined by selecting the weight value with the highest score after the training is completed. So then for the backward pass, I've included first this equation that is the gradient of the loss. So that works to update the scores with the gradient estimation that treats the selection function as the identity function. And then the scores are just updated according to that, which is that second equation I've included. And overall, this is a really simple algorithm, but the results show effectiveness, and they can show comparable accuracy to more traditionally trained neural networks. So the experiments that were set up in this paper, for all of them, the weights were sampled at random from the GLORA uniform distribution, and the scores were initialized independently from a uniform distribution. There were two different data sets. For the MNIST data, 10% of the data was withheld during training as a validation set, and for the CIFAR 10 data, 15% of the data was withheld as validation. So this table just tells some of the architecture specifications of the networks used in the experiments. This first Linné network was just trained on the MNIST data, and all of the other networks were trained on that CIFAR 10 data. And those ones, the ones besides the Linné, are kind of similar to some of the networks that were used in the lottery hypothesis study that I talked about that was done in 2019. So those are just some specifications. So this slide shows some experimental results from the experiments that I talked about on the last slide. Each of these figures compares the test accuracy of a randomly initialized network that basically just performs at random chance to a slot machine network that uses a k value of 2, meaning that there are 2 weight options at each connection. And these results are already really promising because they show that the accuracy improves a lot for the slot machine method over the random chance, even with such a small value of k. And this first figure shows the Linné network, which was trained on the MNIST data. The other 3 were trained on the CIFAR 10 dataset. And all of the results are pretty comparable in how much the slot machine method improved the test accuracy. But you can see that that Linné method does have the highest test accuracy over the other 3. So this paper did also compare the experimental results of changing that k value and how well the model performed in terms of test accuracy. And these figures show that as k, which is the number of random weight options per connection, as that number is increased, the performance of the networks approaches the performance of traditionally trained networks. And the red line on these graphs shows the performance of those optimized, more traditional networks, and then the variance, the accuracy variance for them. So you can see that each of these different slot machine networks does tend to approach the test accuracy of the traditional network, with the Linné and the Conv6 being the most accurate, and then the Conv2 and Conv4 being a little bit less accurate, but still pretty comparable to the traditional network. For the Conv6, it really is only slightly worse than the traditional, so that one tended to be closest. The Linné actually was better than the traditional, but the error bars on these also show that the slot machines have less variance in the accuracy than the traditional networks that were trained by optimizing those weights, which is definitely a good result that shows how competitive this slot machine method is. So some other experiments that were included in this paper, first the slot machines were fine-tuned to see if that might be a good strategy for initializing before traditional training, and it was determined that this resulted in higher accuracy for the Conv4 and Conv6 at no additional training cost, but the other models or the other network architectures didn't really have much effect. It was pretty neutral. Another experiment was just looking at the greedy sampling versus probabilistic sampling, as I mentioned a few slides ago. And it turned out that the greedy sampling outperformed probabilistic. Although probabilistic did maintain decent accuracy, the greedy sampling was also able to improve or stabilize as K increased, which you saw in the last slide. But the probabilistic sampling got kind of unstable as K increased, which isn't really great. So greedy sampling would probably be used moving forward, even though it is slightly more computationally demanding. Finally, an experiment that was done was looking at how sharing random weights impacted the model performance. So the two options that were tested were if all the connections in one layer shared the same set of K random weights, or if all the connections in the whole network shared that same set. However, this kind of resulted in poor performance when K was very small, like if they used a K value of 2, that resulted in worse performance. And there was also a pretty large variance in accuracy between runs. And this is a result from the algorithm having to search in a much smaller space of parameter combinations, meaning that the probability of finding that good combination is reduced significantly. But it was found that the results from these studies were pretty comparable to other pruning methods, so that was definitely an encouraging result of this slot machine method. So finally, the conclusion. Basically, neural networks with weights chosen from a set of random options using a good selection strategy do perform competitively with traditional networks that use optimized weights. And the selected configurations can be used as starting initializations for fine-tuning, although as I mentioned in the last slide, it might help for some, it might not, but it would be worth looking into that if these were used in a real-world scenario. For future work, there should be some analysis of which properties differentiate between selected and not selected weight values when that algorithm is going through and determining how to optimize loss. And also, there should be reduced memory requirements just so that these concepts can be scaled to bigger networks. And on the right, that's just a diagram of what a basic slot machine network might look like. But yeah, so thank you for listening. And I will post my questions along with this video in the Canvas discussion. Thank you. Oh, and here are my references.